Hi. Today, this is the last page of code we made last time. Today we are going to talk about audio in detail, trying to understand what's going on the computer side. And here is the representation of an object moving air molecules in the air. This is what we call a pressure wave, and there is it's moving. Okay, here when some object moves, it makes the air molecules in the air move, and these air molecules become condensed and rare in terms of time. Here rare, condense, rare, condense, and transmitting energy in the air. Then these air molecules hits the bones in our ear, making it vibrate and transmitting some signal to the brain, which we perceive as sound. And we represent this action by a wave. Okay, we take its top point is the compression here. Here 0.0, take it to be the equilibrium, namely the silent point. When it is compressed, we represent it as top point of the wave, where its top point, it's the maximum energy, shows us the maximum point, and the rarefaction, where the molecules are rared, and the bottom point showing us the state where molecules are rared, are the most rared. And here we have normal state, top, normal again, and bottom. Here 4 phases of the wave. Showing us what's going on in the natural world. In this scheme, the sequential 2 top points are considered to be the wavelength, and the top and bottom points, the difference between top and bottom points, is considered to be the amplitude. Okay, this so in representing sound in the air, we actually need 2 variables: how much force is applied and in which direction it is applied. But first, let's have a look what's going on in the computer. We have a permanent movable magnet here, an electromagnet here, and this is the speaker. Our computer makes some electric flow and this electromagnet creates a magnetic field. So depending on the poles, whether they are coincide or they are the opposite poles, this permanent magnet moves, is whether it is attracted or it is repelled from the electromagnet here. And this also makes the air molecules inside the cone move, whether they are condensed or rared. So in this way, if we accurately tell our computer how much force to apply and in which direction, it can use electricity here by creating a magnetic field according to the force variable and direction variable, so making this permanent magnet move back and forth and causing sound by the speaker. So what we need to do is telling the computer the amount of force and direction on the right time. We need a time domain including samples of audio data which tells us how much force to apply and the direction back and forward. And what we need is numbers. But the question is, how can we represent our two variables in numbers? Let's talk about it firstly. Actually, there are two basic ways to do this. First of all, you can use signed numbers. For example, -3, -2, -1, 0, 1, 2, 3. Here, you take 0 as the silent point, and between these and below the 0 you take these numbers as you can use this to show the amount of rarefaction, for example, and above 0 you can use these numbers as amount of compression. So here you can see the 4 states of the audio wave here. Silence, beginning from silence, the maximum compression, and silence again, and then maximum rarefaction. So by using the minus sign here, you can differentiate the direction of the flow, and by using the numbers you can set the force to apply between these two numbers, 3 and -3. You can create periodic waves. Another way is, for example, in this scenario you take the middle term as the point of silence, and again below this middle number you can use these numbers to represent the rarefaction and the amount of rarefaction, and these numbers above silence point you can use these numbers as the amount of compression, and you can represent the wave as a series of numbers. Okay, the bit depth of these number representatives depends on the sample format. Okay, sample format actually gives us available set of numbers. For example, we don't see our sample format here because we take it from the decoder context, but let's suppose that sample format is unsigned 8-bit integer, and this gives us 2/8 numbers between 0 and 255. So we take the 128 as the middle point, and between these numbers we can represent force causing rarefaction and condensation as the amplitude of the wave. Here the amplitude range is the 200 55 numbers, and you take the middle as the silence point, and you can represent the wave here by set of numbers between these two. Okay. So channel layout gives us how many channels, mono, stereo, or maybe more than stereo, and let's look at the buffer size now. We calculated the buffer size before by multiplying the number of samples by the sample format and channel number, and we can do the otherwise also. Let's remember. How much data we have given. This is how much data we have given to the audio callback to STL, and let's calculate the otherwise. Bytes, this is the bits, and we know that sample format is 32 and plus 2 channels, it's 64. Yes, we get the number of samples. On each call we feed the STL with 1024 samples. Yeah. Okay, let's talk about this. Why does STL desires unsigned int 8-bit variable in its callback? Okay, that's the unit number here. This doesn't mean that your sample format should be 8-bit. When you have chosen 32-bit sample format, STL sums up 4 of these to get one sample of data. Suppose let's see the data we have sent to the STL. Okay. See, we are just sending numbers to STL. If our sample format was 8-bit, each of these would be the one sample, and 8-bit also, and mono, each of these would be again one sample. Okay, yeah, you see that this number, for example, says that it is above the equilibrium, so it says that you must compress, you must make the air molecules and the compress this much. For example, this number is almost near the silence point, so the electric flow will be very low in this case. And these numbers, for example, says that okay, now the molecules in the air cone should be released. They should be rare. So make the force the otherwise. Okay. This is all we are saying to our computer. And there is one more point here. Why do we use the expel align here? Because we say that we are going to use this variable very frequently, and we don't want this variable to be fragmented in the memory. So give it much more space when you put it in memory, so that it is much less fragmented in memory. Because when we are to collect this data from memory, if the data is sequential, we will collect it with much less calls, CPU calls. But if it is very fragmented, we will need much more CPU calls and we will lose time. That's why the expel align is indicated here. Okay, that's all.